Hello everyone, thank you for joining. We are Group 11 from Computer Science Department at Bina Nusantara University. Today we will present our work submitted to ICMTech, which is titled Pulmonary Tuberculosis Detection in Chest X-ray Images Using Convolutional Neural Networks for Medical Image Classification. Okay, our problem statement are tuberculosis remains one of the deadliest infectious diseases in the world, causing over 1 million deaths every year, overwhelmingly in low and middle income countries. Chest X-ray is the standard low-cost screening tool for tuberculosis, but reading those X-ray is highly subjective, and there is a global shortage of trained radiologists exactly where the disease burden is the highest. That gap is what motivates an automated, reliable screening system. This is the research gap and our objective. Looking across the literature, we found recurring gaps. Many studies train and evaluate on only a single dataset, which limits generalization. Few explore multi-phase training strategies. Many provide no interpretability, and public datasets often suffer class imbalance. So, we set 5 objectives. Propose a two-phase training strategy with ResNet 50, combine 3 public datasets to reduce single source bias, benchmark fairly against both single-phase and two-phase baseline, validate generalizability with 5-fold cross-validation and cross-dataset evaluation, and provide GradCam visualization for interpretability. Our literature's review summary. In our review, we surveyed 20 studies. A few highlights: Mirugue and colleagues reached 99.4% accuracy with a transfer learned PGG16. Nafisa and Muhammad combined UNet segmentation with EfficientNet V3 for 99.1% accuracy. This is our dataset. We use 3 public available datasets, which are Shenzhen Hospital in China with 662 images, Montgomery County in the United States with 138 images, and a sample subset of Kegel tuberculosis database from Qatar University and the University of Dhaka with 1,400 images. In total, 2,200 chest X-rays, near perfectly balanced, 1,106 normal, and 1,094 tuberculosis.
To the pre-processing and augmentation, every image is center cropped at factor 0.8 to focus on the long region, resized to 224 by 224 and normalized with ImageNet mean subtraction. During training only, we apply augmentation with horizontal flips, brightness and contrast shift, small rotation and zoom. And this is our model architecture. Our backbone is ResNet 50 pre-trained on ImageNet, used as a feature extractor that outputs 7 by 7 by 2048 feature maps. On top, the classification head is global average pooling layer, a dense layer of 256 units with ReLU dropout of 0.5 and a final single unit sigmoid for binary classification, about 525,000 trainable parameters in phase 1. Here is our core contribution. In phase 1, we freeze all of ResNet 50 and train only the classification head with learning rate of 1E4. In phase 2, we unfreeze the top 30 layers and fine-tune with a 10 times smaller learning rate of 1E5. This sequence prevents catastrophic forgetting of the ImageNet features while still slowing domain-specific adaptation to the tuberculosis. Baseline models based on 5 configuration. To prove the two-phase strategy is what matters and not just architecture, we train 5 baseline under identical condition. First, a ResNet 50 single-phase baseline, same architecture but no phase 2, which directly isolates the benefit of fine-tuning. Then PGG16 and MobileNet V2, each trained in both single-phase and two-phase variants. And for our results, on the health our test set of 330 images, our ResNet 50 two-phase model achieved the best result overall performance of all 6 configurations with 92.1% accuracy, 96.6% precision, 87.2% recall, F1 score of 91.7%, and AUK of 97.8%. Two key comparisons. Against the ResNet 50 single phase baseline, phase 2 fine-tuning added 0.3 points of accuracy and over 1 point of AUK, confirming the deeper layers still had the discriminative value to gain. And the same two-phase strategy boosts VGG16 even more, by nearly 3 points of accuracy. MobileNet V2 is interesting outlier, perfect precision but recall is low as 44 to 55%, meaning it misses roughly half of the all TB cases.
Okay. Strong test numbers alone aren't enough. So we validate generalizability two ways. First, five-fold cross-validation on the combined dataset give a mean AUC of 97.48% with a standard deviation of only 0.008. That tells us the performance is stable and not an artifact of one lucky split. Second, we ran cross-dataset validation, train on two datasets, test entirely on the unseen third. Performance drops substantially to a mean accuracy of 67% and AUC of 74%. The best case was training on Shenzhen plus Montgomery and testing on Kaggle. The worst was testing on Shenzhen. Looking at the two phases directly, moving from phase 1 to phase 2 improved our best validation accuracy by 4.24 points and recall by 6.10 points. Training converged in 22 total epochs, and you can see the temporary dip at epoch 11. That's exactly where we unfreeze the layers, after which the model recovers and surfaces. Phase 1, one nuance worth stating, this benefit is architecture dependent. For interpretability, we applied GradCam to ResNet 50's last convolutional layer. For normal cases, activation is diffuse across the lung fields. For TB cases, activation concentrates on the specific regions where opacities, consolidations, and cavities typically appear. Crucially, the model attends to the lung parenchyma rather than background or non-diagnostic regions, evidence that it's learning clinically meaningful features, not shortcuts. We're candid about the limitations. Training was CPU only with no GPU, which constrained architecture size and hyperparameter search. We use center cropping instead of true long segmentation. Our architecture comparison was deliberately basic, no assembles. Cross datasets performance was weak as we showed. And the task is binary. We don't classify TB subtypes or severity yet. FutureWorks follows directly at adding UNet segmentation, test ensemble models, and extend to multi-class TB classification. To conclude, our ResNet 50 model with two-phase training reached 92.1% accuracy and 97.8% AUC. It outperformed all five baseline under identical conditions. Five-fold cross-validation confirmed its stability. We showed the two-phase benefit is architecture dependent and that cross-datasets generalization remains an open challenge. And GradCam confirmed that model looks where a radiologist would. Together, this points to a transparent, interpretable decision support tool for TB screening. That's all for our presentation. Thank you.